I'm telling you a more important thing. None of the algorithms which we are going to talk about in the course are something like just last year or this year or very recent. All of them are about 20 years, 10 years to 15 years old algorithms. But they have become mainstream today because of this particular revolution. That's the power of what we call as the emergence of commoditized, large-scale distributed data engineering frameworks like Hadoop, Spark, etc. Our focus of the course is not necessarily on that because there's a huge new paradigm. But I wanted to clear one important misnomer. Machine learning is not big data. Machine learning can be done on small data also. You may work with small behavior analysis of transactions and come up with reasonable classifiers, or you don't need big data to do machine learning. Big data is real in several cases, but let's not get confused by saying that we need Hadoop for machine learning. We don't need. You can run it on good, decent hardware, decent machine learning framework. If you have large data, then you may have to port such framework on a large Hadoop file system or on a large Spark system. But we will be covering in the last part of the course. My colleague will cover on the big data ecosystem in brief, especially Hadoop and Spark ecosystem. But given that we have covered most concepts of the business dimensions, I'll briefly cover some guiding dimensions of what we do in machine learning. There are broadly two dimensions on which we classify: unsupervised or supervised. In unsupervised, it's effectively like we don't have the notion of a model or a target function which we do at the end of it. All we try to do is we identify hidden patterns. There's no notion of specific model which will be used for predicting output for a future query. Here the notion is you either identify groups of similar data, cluster similar inputs. Let's say you have a gathering of a lot of Indian community in for a religious event. You try to create, say, cluster of people who are kind of eating similar food, maybe vegetarians, vegetarians, non-vegetarians. So you try to form clusters of people based on that. You don't necessarily explicitly classify saying that one guy is this, one guy is that. You don't have a model saying that if one person behaves like this, you will be classified as a way. You don't do that. But if you have a new input, you try to fit the new person into one of these approximate categories you have discovered. So a lot of times what people do is when they don't have an idea of the model given raw data, they actually look at how you can use unsupervised learning to identify clusters, and then they try to use some further more formal supervised learning methods. Typical techniques are things like k-means clustering is a very common example. We have hierarchical clustering, top-down clustering, all kinds of examples. Then we have examples of another example which I was telling you about retail, right, where people talking about buying items together. That's more like an association. An association rule defines a correlated set of items, also known as frequent item sets, which people buy together in typical retail transactions. So identifying such associations, whether it is an associating retail transactions, or it could be used in things like what are the typical symptoms which go together in a healthcare scenario, all that is useful. In case I was giving an example of recognizing a cat in a large collection of YouTube videos, here you don't create a model, but you just use raw data to create something known as collection of these features typically will mean that this is a cat. So feature extraction technique is a very useful technique in unsupervised learning for dealing with large corpus of raw data. So unsupervised learning is very critical in several scenarios where you don't have a notion of prior function or model. Whereas in several scenarios, we try to identify what is known as a function, a pattern, or a model. There we divide the category or raw data. First we label it, saying that this is the output, this is the input set of variables, this is the raw data. And then we try to say that, okay, for part of the data, let's say 80% of the data, we take it and run our algorithm and then generate a model. Then part of the data, which is 20%, which is test cases, test data, we try to identify how well it is able to predict the output in the test data. Then based on that, we can iterate back and forth by trying different algorithms, by trying different combinations of training and test data, different samples, etc. Somewhere where you are reasonably confident this is the best you can do, that's why you say that this is the model you come up with the given current data. And then you output that model, that is what becomes your learned model for your raw data. For the future data that comes in, you'll apply that model, and for the input set of data for that sample, the output will be generated based on applying the model to the appropriate values or the input variables. So accuracy could be defined by number of correct classification by number of test cases, typical example. But here, important thing is this whole training test is very important. You have to classify the data into training component, test component. And here again, there is one more difference I would like to point out, which is classification versus regression in a supervised case. The model which you're talking about could be something like a function. It could be a straight line, or it could be a hyperplane, a function of some y equal to fn x1 plus f2 x2 or something. That's what we call regression. Or it could be a classification, saying that, okay, I look at all my Twitter sentiments and I look at, okay, either this could be a neutral, it could be a positive sentiment, it could be negative sentiment. So here in classification, we have predefined notion of a set of categories, and the target variable is categorical. In the sense, this is basically falls into these specific categories. So in classification, we talk about categorization into specific categories which are predetermined. So we create a model, and then when a new data comes in, depending upon the graph which you have, you can put it into the right category where the input falls, and then the output will be the category to which it will belong. In regression, on the other hand, it's a variable, continuous variable. Output will be a specific value of the output variable, which when applying that model or the function which is generated to the input variables. So pictorially, you can see this. It's like this. Classification is more like you have categories into which you bifurcate or trifurcate or multiple. In regression, you create a function. With that, I stop here. We'll take any